we will conclude our video lecture series for thermodynamics this semester with a look at multiparticle systems handled in the Grand Canonical Ensemble. There's not too many concrete results that we can get from here because it's important what the system actually is. But there's a lot of theoretical, qualitative results that we can get that are very powerful and begin to show the links of thermodynamics and statistical mechanics to the wondrous advances that happened in the 20th century. Superconductors, superfluids, electronics, transistors, these all work at finite temperature, and to understand what's going on with their quantum particles that makes them work, we begin with the Grand Canonical Ensemble. First, let's look at Bose systems. A Bose system is one where the particles can occupy energy states. We let K be the label of a given energy state with energy epsilon sub K. The total energy contributed by particles in this state would be the energy of that state multiplied by the number of particles in that state, lowercase n sub k. Since we're dealing with a quantum system, we may have multiple particles in the same energy state. You can think of this as multiple particles in a quantum potential well existing at the same energy level, or the number of photons in a box having the same wave number. To calculate the grand partition function of a Bose system, we need to sum over all possible energy states with a summand equal to the Gibbs factor, exponential of minus beta ek minus mu nk, lowercase nk, over all possible states. By summing over energy states instead of each specific particle, we make these systems possible to calculate. Here's how it works. When we sum over all states, what do we mean? Every microstate of the system could be specified by saying how many particles are in each energy state, whether it be 2 particles in state 1, 3 particles in state 2, 4 particles in state 5. That set of integer numbers tells you what the microstate is. So to sum over all states, we can sum over the number of particles that are present in each state. And for a Bose system, there is no restriction on how many particles occupy a given state. So these sums will go from 0 to infinity. And they're actually an infinite number of sums because there are an infinite number of energy states at higher and higher energies. However, the partition function is still well defined. For each state, we have a number of particles in that state. And we have an exponential of the number of particles in that state times the energy of that state. Go with state 0 first, minus the chemical potential times the number of particles in that state. So we have one term like this for each energy state. And there are an infinite number of products of these. The products of exponentials come from expanding the total energy sum and the total particle number sum inside of the exponent. Each of these terms, though, can be viewed as an independent sum. And so our total grand partition function can be done with geometric series. Again, we see n0 multiplies both terms in here. So the sum over n0 is a geometric series. And the same for n1, and the same for n2. So we will get the product of a bunch of geometric series sums. 1 over 1 minus the exponential of minus beta E0 minus mu times another factor, 1 over 1 minus e to the minus beta, this time with energy level 1. And an infinite product of these, one product for each energy state that the system possesses. This infinite product actually does result in something useful. To continue towards thermodynamics, we have to take the natural log of this grand partition function. When we take this natural log, we turn our product into a sum over the energy states. And the term in the sum is the log of basically this denominator, 1 minus e to the minus beta epsilon k minus mu. Now, without specifying the spectrum of energy states, epsilon k, we can't really do this sum. But it turns out we can make many important conclusions without doing the sum at all, because the number of particles in the system is equal to the negative derivative of this grand potential with respect to its chemical potential. And this grand potential is equal to negative kT log of the grand partition function. So let's do this operation here. The two negatives will cancel. We'll end up with a positive kT times the derivative with respect to mu of this entire sum. And we have a minus sign here, here, and here. So there's one minus sign out front. And then when we do this derivative, we have a significant number of more minus signs that enter. Let's be careful. So first, we have a logarithm, so it's 1 over the thing inside the function. And then we have a function inside here, so it's the derivative of that, so minus exponential. And then we have the derivative of the exponent from the chain rule. With respect to chemical potential is going to give us plus beta. So all this looks like quite the mess, but it will in fact simplify to something quite a bit nicer looking. The minus signs here and here cancel. The kBt and the beta cancel because they are inverses. And this exponential here can be rolled into this product in the denominator to give us an exponential with a positive beta, ek minus mu, minus 1. So this is just a formula for the total number of particles in the system as a function of chemical potential. But we can interpret it to mean much more. What we're seeing here is a sum over the possible energy states of some quantity that depends only on that energy state. So it's reasonable to expect that this quantity represents something about the number of particles in that energy state. We interpret this sum as meaning the sum over all states of the average number of particles in that state. We call these values n sub k the occupation numbers. And the distribution of these occupation numbers is called a Bose-Einstein distribution. Notice that the Bose-Einstein distribution can easily be greater than 1. If the value of epsilon and mu are close together, the exponential can be close to 1. When a 1 is subtracted from that, it may leave a very small number in the denominator. So we see in a Bose-Einstein distribution, occupation numbers can range from 0 to any positive number. To get a better feeling for what the Bose-Einstein distribution means and how we can make some qualitative conclusions from it, let's interpret it on a graph. Versus energy. And we'll label at some point the chemical potential value mu. Notice what happens at a point when the energy of a state is close to the chemical potential. If the energy of the state is just slightly greater than the chemical potential, then the exponential here will be just slightly greater than 1. And when we subtract 1, a small number appears in the denominator, leaving a large value. In fact, as epsilon approaches mu from above, or as mu approaches epsilon from below, the occupation number rises without bound. It has a vertical asymptote. Bose-Einstein distribution, then, has a vertical asymptote at E equals mu. Since there may be multiple states in our system of different energy levels, we really must have a chemical potential value that is lower than the minimum energy level in the system. Mu must be lower than what's called the ground state energy, E0, for that system. If this was not the case, then some energy with a level below the chemical potential would be predicted to have a negative occupation number, which is unphysical. Therefore, the chemical potential in a Bose system must always be lower than the ground state energy. We usually say it must be negative and set the ground state energy to 0. Now, if we look at the effect of temperature, you'll see that it acts similarly to the Boltzmann distribution. In a low temperature distribution, there is a lot of tendency for occupation numbers that are low energy to be high. But as the temperature increases, this distribution becomes much wider. And particles can be more often found with high energy values. So if the energy is very high and much higher than mu, the Bose-Einstein distribution can look very similar to a Boltzmann distribution. It's basically exponential if this 1 is neglected. But we always have to remember that at lower energies, we can start to get weird behaviors in the Bose-Einstein case. Let's look at one of those weird behaviors, which gives us a window into the dizzying array of crazy phenomena that we can see with quantum systems. This is called Bose-Einstein condensation. As we lower the temperature of a system or increase its chemical potential, the states which have an energy just a little bit above mu become more and more populated with particles. Eventually, we can reach a point where there is one state with the lowest energy whose energy is so close to mu that the number of particles in that single quantum state grows to a macroscopic fraction of the system. If we lower the temperature or raise the chemical potential so much that it gets close to the ground state, then N0 can become much, much greater than 1, on the order of Avogadro's number, actually. Normally, in a multi-particle system, we don't have an appreciable number of particles in any specific state. If I asked you, in an ideal gas, how many particles are traveling at exactly 1 meter per second to the left, the answer would be 0. They've all got some small velocity that makes it impossible to have any specific value. But in a quantum system, where we can have a specific state with a specific energy, if it's filled with bosons, they can have an enormous number of particles in that same quantum state. And that leads to some weird behaviors. So a same quantum state has a large number of particles. And those particles then begin to act like they are a single quantum state itself. They have a wave function, they obey interference. It's like we've taken quantum mechanics and blown it up to real-size proportions. This behavior of Bose-Einstein condensation is the thing that underlies the physical observations of superconductivity and superfluidity. Both of these phenomena defy our everyday experience because they are a quantum property blown up to real-size proportions. The second thing that we'll look at is Fermi systems. Again, we will use the Grand Canonical Ensemble. It's treated very much the same way as a Bose system. The only difference is the Pauli exclusion principle means that the number of particles in any specific state can either be 0 or 1. We cannot have two particles in the exact same energy state. That is the Pauli exclusion principle. So when we do our grand partition function and sum over all of the values for the number of particles in a given state, we don't sum from 0 to infinity, we sum only from 0 to 1. The terms in our sum are the same. Exponentials of minus beta E0 minus mu times the number of particles in that state, a product infinitely long for all states. And when we do this sum, it turns out to look very similar again to the one for bosons. When we sum from 0 to 1, when the n is 0, we just get a 1 for the exponential. When the n is 1, we just get the exponential itself. So what this looks like is a product of 1 plus exponential of minus beta epsilon minus mu over all the states. We do the same thing we did before. We take the natural logarithm of this and multiply by kT to get the grand potential. The grand potential for this system is then positive kT times the sum over all energy states of the natural log of 1 minus e to the minus beta epsilon k minus mu. Our main conclusions qualitatively will come from finding out the formula for the number of particles in this system. This derivative reduces to something very similar to the one for Fermi systems. Oh, I might have miscopied here. We've got a minus here, please excuse me, and a plus here. I had actually copied down the one from Bose Systems, just again, without flipping the page. This is the one for Fermi systems, and I assure you we could all get there from taking the log of this. So when we get to our formula for the particle number, then we have a very similar factor here, exponential of beta epsilon k minus mu, but the minus 1 has now turned into a plus 1. It's the same plus 1 from here and from the whole sum. Just a small change of sign, right? That can't make it so different. But the Fermi distribution that we see here has a totally different behavior from the one for bosons. Let's write out the occupation numbers are 1 over epsilon k minus mu times beta plus 1 and think about some of the implications of this formula. Again, we'll try to draw it out as a graph with a mu value marked at some point. When the energy of a state is equal to the chemical potential, or the chemical potential is equal to the energy of a state, the exponent is 0, and the exponential is 1. This doesn't cause a problem for the Fermi distribution. 1 plus 1 is 2, and 1 over 2 is 1/2. So the chemical potential is the point where the occupation number takes the value 1/2. If we look at energy levels that are less than the chemical potential now, we see epsilon minus mu would be negative, and the exponential of a negative number is less than 1. So when we add 1 to it, we make something that is a little bit larger than 1. Definitely larger than 1/2, because we're adding 1 to some number in the bottom. So when epsilon is less than mu, the occupation number in that state is greater than 1/2. And in analogy, when the epsilon energy of a state is greater than the chemical potential, the occupation number is less than 1/2. If the energy is much, much less than the chemical potential, then this exponent is extremely negative, and the exponential is equal to 0. So the occupation number tends towards 1. And if the energy value is much, much greater than mu, this exponent is very highly positive, and the exponential is even more positive. The plus 1 virtually doesn't matter, and we have an occupation number that tends towards 0. The dividing line between those two behaviors occurs at the chemical potential value. So the Fermi Dirac distribution looks like this. And this is the distribution that's obeyed by fermions, like electrons in atoms or electrons in metals. It has a very peculiar behavior. First, let's discuss how it behaves with regards to temperature. At a high temperature, the effect is basically to spread out the distribution over a wider range of energies, the same as it did for the Boltzmann and Bose-Einstein distribution. Higher temperature means more spread of particle probabilities. At low temperatures, the distribution becomes less spread out, but it still has to go to 1 at the top or at the left and down to 0 at the bottom. So in the limit of low temperatures, the Fermi Dirac distribution has an entirely different behavior to other distributions. It looks almost like a step function. 1 if the energy of the state is less than mu, and 0 if the energy of the state is above mu. So let's write that out. At low temperatures, Nk equals 1 if the energy of that state is less than the chemical potential and the state is basically unoccupied if the energy level is greater than the chemical potential. So the chemical potential here acts as kind of a sliding bar where we can set the point of the cutoff between occupied states and unoccupied states. Fermi himself had a name for this behavior where all of the states below mu would be occupied. He called it the Fermi Sea. It's like the ocean, where all the elevations below the surface are completely full of water molecules, and everything above it is completely empty. There's a sharp dividing line. An important application of this Fermi Dirac distribution can be the electrons in atoms. In chemistry courses and in high school, you learn that atoms have electron shells and electron orbitals, and those shells get filled up, starting with the lowest energy ones first, building up, not usually leaving any gaps, filling up all the shells until there's enough electrons in that atom. The Fermi Dirac distribution explains to us what happens to that situation as the temperature is increased. If we have a low temperature relative to our atomic energy levels, all the energies below some cutoff point will be full of electrons, and all the energies above will be utterly empty. If we heat up the atom and raise its temperature, we start to get a possibility of getting some electrons having a probability in states that are above the cutoff, and some probability for having empty shells in states below the cutoff. This is why atoms glow when they get hot. There's probability for the electrons to jump around between these energy states that are near to the cutoff. Every time they jump, they release some radiation as light. A second cool application of the Fermi-Dirac distribution is in the theory of metals. In a metal, the energy levels for exciting electrons are usually much higher than the chemical potential. Or not higher than, they're usually much higher than the temperature. So your epsilon values are much higher than kT. You can figure this out by taking a normal work function for a metal. It's about 2 to 5 electron volts. And taking the value of kT at room temperature, it's about a 200th of an electron volt. So this means that for metals, the Fermi-Dirac distribution is very sharp. Everything below is occupied, everything above is unoccupied. That's mildly interesting on its own, but it comes into huge importance when we start considering the band theory of conduction, or of semiconductors. The way the band theory works is by asking the question of what energies are allowed. What are the energy states that are allowed in a metal or solid system? The result, which is hard to prove, is that the energies have a jump in them, a discontinuity. For certain k values, you'll get a range of energies possible, and then suddenly you will go up to a different branch of the energy. This means that the energy spectrum of allowable energies has a band structure. Electrons can have any wave vector that they want, but they can't access certain energies inside these gaps. So we have bands where the electrons can have an energy, and then we have gaps. One of the ways that we can explain the conductivity of metals and solids is by the value of the chemical potential. If a solid naturally has a chemical potential inside of one of the bands, it means that it's very easy for an electron to just gain a little bit of energy and still be at an allowed place. But if that solid has a full band and the chemical potential is in between in the gap, then it means that in order for an electron to get excited to a different band, it has to jump the entire gap of energy to become a mobile electron. This doesn't do nearly a service to the entire theory of conduction in metals, but at least we can tell from the Fermi-Dirac distribution that the chemical potential acts as sort of a sliding level where the electrons can fill up all the spaces below it and not go into all the spaces above except for a narrow range. One of the things that's done in the creation of semiconductors is to add small bits of impurities called dopants to the crystal lattice that can control the value of mu. Some semiconductors also have their value of chemical potential related to their voltage. So by applying a certain voltage or electric field, this chemical potential may move in or out of a gap or a band, allowing us to change the conductivity drastically by altering the external electric or magnetic fields. So that's just a sort of a preview of the more interesting sorts of quantum physics phenomena that come bubbling up from statistical mechanics of quantum particles at the macroscopic scale. We can use the Grand Canonical Ensemble to begin to make conclusions about these multi-particle systems. There's a difference behavior between bosons, which can have any number in a state, and fermions, which can only have 1 or 0 in a state. And the applications of these to modern technology are huge.